and the motor. The motor is an electrical induction motor which allows us to convert electrical energy into mechanical energy. This mechanical energy is used to drive the pump and move the water. The pump pulls water in through the inlet and pushes it out through the outlet. As we take the unit apart, we can see that we have a fan and a protective casing mounted at the back of the electrical motor. Then inside the motor we have the stator. The stator holds the copper coils, and we're going to look in detail at that a little later in this video. Concentric to this, we have the rotor and shaft. The rotor rotates, and as it rotates, so does the shaft. The shaft runs the entire length from the motor and into the pump. This then connects into the pump's impeller. Some models of centrifugal pumps, like this one, will have a separate shaft for the pump and the motor. Separated shafts are joined using a connection known as a coupling. Coupled pumps will usually have a bearing house which, as the name suggests, houses the bearings. The shaft continues into the pump casing. As it enters the casing, it passes through a gland, packing and the stuffing box which combine to form a seal. The shaft then connects onto the impeller. The impeller imparts centrifugal force onto the fluid which enables us to move liquids such as water through a pipe. The impeller is enclosed within the pump casing. The casing contains and directs the flow of water as the impeller pulls it in and pushes it out. Therefore, we have a suction inlet and a discharge outlet. At the back of the electrical motor, we see that the fan is connected to the shaft. When the motor rotates the shaft, the fan will therefore also rotate. The fan is used to cool down the electrical motor, and it will blow ambient air over the casing to dissipate the unwanted heat. If the motor becomes too hot, the insulation on the coils inside the motor will melt, causing the motor to short circuit and destroy itself. The fins on the outside perimeter of the casing increase the surface area of the casing, which allows us to remove more unwanted heat. The electrical motor comes in either 3-phase or single-phase configuration, depending on the application. We're going to look at 3-phase as this is the most common. Inside the 3-phase induction motor, we have 3 separated coils which are wound around the stator. Each coil set is connected to a different phase to produce a rotating magnetic field. When we pass AC or alternating current through each coil, the coil will produce an electromagnetic field which changes in intensity as well as polarity as the electrons passing through it change direction between forwards and backwards. But if we connect each coil to a different phase, then the electrons will change direction between forwards and backwards at a different time compared to the other phases. This means that the magnetic field of each coil will change in intensity as well as polarity at a different time compared to the other phases. To distribute this magnetic field, we rotate the coils 120 degrees from the previous phase and insert them into the stator of the motor casing. This will create the effect of a rotating magnetic field. At the center of the stator, we place the rotor and shaft. The rotor will be affected by the rotating magnetic field and will force it to also rotate. The rotor is connected to the shaft, and the shaft runs from the fan through the rotor all the way up to the impeller. This way, when the rotor rotates, so will the impeller. So now, by creating the rotating magnetic field within the motor, we spin the rotor, which spins the shaft, and this spins the impeller. Looking at the pump casing, we find a channel for water to flow along, which is called the volute. This volute spirals around the perimeter of the casing up to the pump outlet. This channel increases in diameter as it makes its way to the outlet. The shaft passes through the seals and into the pump casing where it connects to the impeller. There are many types of impeller, but most will have these backward curved vanes which will either be open, semi-open or closed with some shrouds. These backward curved vanes do not push the water. The curves rotate, with the outer edge moving in the direction of the expanding volute. These vanes will provide the fluid with a smooth path for the water to flow. We'll see that a little later in this video. The impeller is submerged in water. When the impeller rotates, the water within the impeller also rotates. As the water rotates, the liquid is radially pushed out in all directions to the edge of the impeller and into the volute. As the water moves outwards off the impeller, it creates a region of low pressure which pulls more water in through the suction inlet. The water enters into the eye of the impeller and is trapped there between the blades. As the impeller rotates, it imparts kinetic energy or velocity onto the water. By the time the water reaches the edge of the impeller, it has reached a very high velocity. This high-speed water flows off the impeller and into the volute, where it hits the wall of the pump casing. This impact converts the velocity into potential energy or pressure. More water follows behind this, and so a flow develops. The volute channel has an expanding diameter as it spirals around the circumference of the pump casing. As it expands, the velocity of the water will decrease, resulting in pressure increasing. This expanding channel therefore allows more water to keep joining and converting into pressure. So the discharge outlet is therefore a higher pressure than the suction inlet. The high pressure at the discharge allows us to force the fluid through pipes and into a storage tank or around a pipe system. The thickness of the impeller and the rotational speed affects the volume flow rate from the pump, but the diameter of the impeller and the rotational speed will increase the pressure it can produce. Centrifugal pumps are represented in engineering drawings with symbols like these. They can vary slightly from this, so do check the drawings information section. NPSH. A term you're going to hear is the NPSH, which is the acronym for Net Positive Suction Pressure. We'll briefly cover what this means. There are two letters at the end of the acronym, the NPSHR and the NPSHA. The R is the required NPSH. Each pump is tested for this value, and this can be obtained from the pump manufacturer via the pump's operating chart. Don't worry about this confusing looking chart at this point. We're going to break it down and cover that in detail in a dedicated video. Links to that in the video description down below. The R value is basically a warning or danger point. As the water enters the pump and flows into the impeller's eye, it experiences a loss of energy due to the friction. This will give us a pressure drop. At certain conditions, the water flowing through this section can reach boiling point. When this occurs, we refer to this as cavitation. We're going to see more on that in just a moment. The other letter was the A, and this is the NPSH available. This depends on the installation of the pump and needs to be calculated. It considers things such as installation type and elevation, liquid temperature, liquid boiling point, etc. The available pressure should always be higher than the required value. For example, if we have an installation and we calculate the NPSHA as 11, but the pump requires an NPSHR of 4, then the pump should be okay. However, if we installed a pump that required an NPSHR of 13, then the available NPSH is insufficient and cavitation will occur. So what is cavitation? As we know, water can turn from a liquid state into steam or a gas state. We know that water boils at around 100 degrees Celsius, and that's because it's at sea level, which has an atmospheric pressure of 101.325 kPa. But if we went to the top of Mount Everest, then water boils here at just 71 degrees Celsius, and that's because the atmospheric pressure has reduced to 34 kPa. As the atmospheric pressure reduces, it becomes easier for the water to boil. So at the suction inlet of the pump, we know that there is going to be a pressure drop. And if this pressure is less than the vapor pressure of the liquid being pumped, then the water can reach boiling point. When this happens, cavitation occurs. During cavitation, air particles within the water will expand as they reach boiling point. These will then collapse in on themselves very rapidly. As they collapse, they will damage the impeller as well as the pump casing. This removes small parts of metal from the surface, and if this keeps occurring, then it will eventually destroy the pump. Therefore, we must ensure the available pressure is higher than the required pressure of the pump. We use centrifugal pumps everywhere. We use them to move liquids from one tank to another or around a system. For example, we might use a small inline centrifugal pump in our domestic heating circuit to move heated water around the property. We might use a large centrifugal pump to move